We build massive data centers that stretch across entire landscapes, but the real engineering happens at the nanoscopic level, down at 3-nanometer transistor grids. There is a strange contradiction in modern computing. The tech industry is obsessed with making devices smaller, yet the physical tools required to build them are growing unrecognizably large. This is an ASML Extreme Ultraviolet, or EUV, lithography scanner. It is a maze of brutalist metallic complexity, and the only reason the most advanced chips on Earth even exist. This contrast between a microscopic product and a macroscopic machine creates the primary bottleneck of modern technology. It will dictate whether the progression of computing can continue or if it stalls entirely. To print these chips, today's machines perform a bizarre mechanical ballet. They fire carbon dioxide lasers at droplets of molten tin, 50,000 times a second, inside a vacuum chamber, just to generate flashes of invisible EUV light. The process takes immense energy, but after all that mechanical effort, less than 0.1% of the usable light actually reaches the silicon wafer. This animation illustrates exactly what happens at the 3-nanometer scale when we start running out of light. It's an effect called shot noise. Imagine trying to spray paint a perfectly sharp line on a grid, but the paint particles are too sparse. They hit the target randomly, creating jagged, uneven edges. We cannot fix this lack of light simply by exploding more tin. The physics demand a different approach to generating light if we want to keep shrinking transistors. To generate exponentially more light, the semiconductor industry has to stop relying on atomic physics, like hitting tin droplets, and pivot to the raw speed of particles in motion. A free electron laser fires electrons near light speed through a linear path of alternating magnets, forcing a violent zigzag. As they navigate these curves, they group into tight bunches, emitting a powerful beam of extreme ultraviolet light. To generate light this way, the machinery must scale up to the size of particle accelerators, stretching for kilometers underground. Moving to free electron lasers shifts semiconductor manufacturing away from traditional mechanical engineering and into the realm of high-energy physics, requiring infrastructure on the scale of a national laboratory. The sign here for the SLAC National Accelerator Laboratory represents the pedigree behind the American strategy. A company called xLight is working to adapt decades of accelerator research into a commercial design. Their specific goal is to keep the existing ASML manufacturing scanners, but replace the tin blaster with a linear accelerator that pumps out 4 times the light at a lower operating cost. Japan is taking a different route. Researchers at Keck are focusing strictly on electrical efficiency. They're developing an energy recovery linac. It acts like regenerative braking, but for particle accelerators. Instead of dumping waste energy, the system loops electrons back around, so their remaining momentum helps power the very next beam. Meanwhile, researchers connected to China's Tsinghua University are ignoring size limitations and the architecture of existing factories entirely. This comparison illustrates the 3 approaches. Left is the American linear add-on, middle, the folded Japanese regenerative loop, and on the right, the Chinese strategy, massive circular storage rings designed to feed multiple scanners simultaneously and bypass Western technology sanctions. The race for the next microchip is no longer confined to etching silicon. It has become a global competition to see which nation can build the most effective industrial system for controlling light. Despite the theoretical elegance of particle accelerators, ASML's exploding tin systems will dominate the immediate future. This manufacturing floor highlights the brutal economics of the industry. Theoretical efficiency means nothing if an unproven particle accelerator fails and freezes a billion-dollar production line. Fabs demand 24/7 reliability, and ASML's machines are already proven. You can see the urgency at TSMC's Fab 21 in Arizona. The demand for AI chips means physical infrastructure is going up right now. The industry requires advanced manufacturing capacity immediately, not in another decade. In manufacturing, a complex machine that successfully operates today will always beat a superior concept that belongs to tomorrow. But eventually, the physical limits of our current light sources will be exhausted, forcing a total evolution of the chip plant. the future chip factory functions as a massive hybrid complex, a manufacturing floor integrated with a dedicated power plant and a CERN-style particle physics facility, all sharing one central light generator. To continue printing the smallest devices in human history, our only remaining option is to construct the largest factories ever conceived.